Let's analyze the story for the group 2 cations. Okay, so this particular metal ions are the ones that reside mostly at the bottom of the periodic table, right? But we have copper, germanium, arsenic, and selenium that also get incorporated with these metals. And the reason why is because of the reactivity that they possess. It's very similar in terms of you getting a precipitate out of these metal ions. And typically what gets to be done in the, or at least what used to be done in the laboratories was that you would add H2S solutions to these elements to precipitate them out. But you would do it such that the pH was low. So this would be an acidic solution of H2S. And nowadays we don't use H2S too much to carry out this particular process because H2S is a very stinky reagent, and at high enough concentrations is actually poisonous. So we tend to we have drifted away from using this particular reagent, and we use different other reagents. But if you look at typical problems, they usually still have you do the investigation with acidic H2S. And the idea is that each one of these transition metals or main group metals, when in combination with sulfide, you end up forming an insoluble sulfide salt like copper 2 sulfide or cadmium sulfide or copper 1 sulfide or antimony 3 sulfide. Each one of them has a KSP value that is very low. Although mind you, for some of them the proportions are not 1-to-1, so they could be a little misleading even though they may seem super slow or super low in value. So I want to focus on the copper just to give you a proper example. Alright, so copper, if you add H2S to it, you're going to have some concentration amount of sulfide that can precipitate the copper. And as you can see, the KSP value is very low. This is a 1-to-1 ratio of cation and anion, so this looks definitely pretty low for those low ratios. But the thing is that you're not adding sulfide to the copper solution, you're adding H2S. And we know that to be true because the pH is acidic, so you're going to favor the conjugate acids over the conjugate bases. So what we need to also investigate is the acid-base chemistry of H2S. H2S can donate a proton, since it's an acid, and in the process it forms hydrogen sulfide, which itself can donate another proton and form sulfide altogether. And each one of those two processes has a Ka value associated with it. Alright, so what we're going to do is we're going to utilize these three equations to look at the idea of forming the copper solid salt, which ultimately means that we need to reverse that equation. Right, so we're actually interested in finding out how do we make a solid out of this, how do we precipitate it out, since that's what happens when you add acidic H2S. So we reverse the equation, and by default what we need to do is raise that KSP to the -1 power. Alright, now if you look carefully though, what you're going to realize is that yes, okay, so the KSP changes to this really high positive value, value greater than 1. Okay, so what happens now is that if you add these equations together, the sulfides cancel out. And the hydrogen sulfides also do cancel out. And basically what you end up with is the actual reagents that you start with, the copper 2+, the H2S, the copper sulfide that you may be forming as a precipitate, and then the protons that are generating the, basically that leading to an acidic solution, to the lowering of the pH. So this looks very likely as to what's happening in that specific flask when you add the H2S to your copper solution. So let's figure out what happens to the equilibrium constant. We have already applied the -1 power to the KSP, so we now can multiply the equilibrium constants together to yield the new equilibrium constant for the final equation. So we have 1.25, so here I've included the extra digit that I didn't have right here, times 10 to the 36, 1.1 times 10 to the -7, and 6.2 times 10 to the -8, which generates a value of 8.53 times 10 to the positive 21. So this reaction, just by looking at the equilibrium constant, tells you, yeah, this wants to happen. This is very likely to happen. And the value is so much higher than 1 that you actually don't even require much of a concentration of sulfide to make this happen. Just with H2S alone, you could make this happen, no problem. So typical concentrations and conditions that make this happen are concentrations of 0.02 molar copper 2 plus, concentrations of 0.02 molar H2S at a pH of 1. And if you apply the equilibrium expression for this equation, you have H plus to the second power divided by copper 2 plus and divided by H2S. Those are the only aqueous species in this equation. If we input the values that we have here for the typical conditions, and of course change the pH to hydronium concentration, in other words raise 10 to the negative 1, 10 to the negative 1 being 0.1, we have 0.1 molar squared divided by 0.02 divided by 0.02, which tells you that the Q value is 25. And looking at the equilibrium constant, we can see that the value of the equilibrium constant is higher than Q. And because of that, this reaction is product favor, meaning that it will go to form a precipitate. So you can see just from the conditions that we use and the equilibrium value that we can actually make a very positive claim as to why we're forming this precipitate in the first place. Alright, let's take a look at the group 3 ions and see what happens with them. Okay, as I pointed out before, the group 3 ions correspond to the vast majority of the transition metals and also the lanthanides and actinides. These particular ions don't precipitate with acidic H2S, but instead they precipitate in the presence of basic sulfides like ammonium sulfide solutions. And to give you an example, I'm going to focus on nickel, which is one of the ions in the group 3 metals. Nickel 2 plus reacts with sulfide to give you nickel 2 sulfide. We have a KSP for that process of 3 times 10 to the negative 16, and once again, by definition, KSP starts with a solid yielding the soluble species. So what we do is we look at the once again the process of H2S deprotonating, ultimately yielding the sulfide. And what we did before for copper, we applied also to nickel, meaning that we're going to reverse the KSP equation, which means that we will raise the KSP to the negative 1 power. So I kind of want to show you that again. It used to be 3.0 times 10 to the negative 16. Reverse the equation means that you're going to raise that value to the negative 1 power, and so now we have 3.33 times 10 to the positive 15. If we add it together, the sulfides cancel out, the hydrogen sulfides cancel out, and we end up with a similar equation that we had, except that instead of copper, now we have nickel 2 plus. Multiplying the equilibrium constants together tells us that the value of this equilibrium constant is barely 20.6. So applying the same conditions that we had before for copper means that the Q value that we're going to get is still 25. That'll be the case because we didn't change the numbers whatsoever. But this is a low pH, so what you can see right here is that Q is larger in fact than K. Not by a lot, but it is still larger than K, so this is actually favoring the reactants. So at low pH, you do not precipitate nickel, which is kind of good because that means that you will only precipitate your group 2 metals as opposed to your group 3s. So keeping the pH low when you add the hydrogen sulfide is key to preventing the group 3 metals from precipitating out. But if you start increasing the pH, meaning that the concentration of H plus becomes smaller and smaller, you will make the value of Q smaller than K, and at that point the reaction goes forward and produces your precipitate. So it's kind of cool to see quantitatively how that works out. And that's kind of the idea that I'm trying to convey to you guys by applying this complex equilibria, this mixed equilibria idea to simple chemistry associated with qualitative analysis. Alright, in the next video I'll finish this up by looking at group 4 and group 5.